Chemistry, we're moving into our second lesson in Unit 4 for intermolecular forces. Here we're going to learn how to analyze intermolecular forces, the different intermolecular forces, and determine which have the most influence on the molecules. So boiling point is a good indicator of the strength of intermolecular forces because it means that more thermal energy heat is needed to separate the molecules. So if two molecules have strong intermolecular forces between them, it'll take more energy to pull them apart, and that energy is in the form of heat, and that can be measured by the boiling point of the substance. We will look at how London dispersion forces, dipole-dipole forces, and hydrogen bonds affect the boiling points of different molecules involving the four halogens, and you see them over there in green: fluorine, chlorine, bromine, and iodine. Let's examine which halogen molecule has the highest boiling point and how this is explained by intermolecular forces. So look at these diatomic halogens. So all molecules have London dispersion forces, LDF. Nonpolar molecules have only London dispersion forces. Halogens form nonpolar diatomic molecules. Be sure you understand why. Two fluorine atoms have exactly the same electronegativity. One of them is not stronger than the other, so they pull on the electrons equally, and therefore they share them equally. So that's going to be nonpolar. You won't have the electrons pulled to one side or the other. The same is true of a chlorine molecule, a bromine, and iodine molecules. Now these four molecules, remember, are four of the 7 elemental diatomic molecules. In nature, they always form pairs and form molecules. So you'll never see a single fluorine atom floating around in the atmosphere. It's always going to be an F2. It's going to pair up with another fluorine and form an F2 molecule. Same with chlorine, bromine, and iodine. As a nonpolar halogen molecule becomes larger, it gains orbitals and electrons. Large nonpolar molecules are more polarizable because they have many electrons that can easily be pushed to one side. So the more electrons an atom has or a molecule has, the more that they can be pushed to one side by a whole lot of electrons from another molecule. And so that's said to be polarizable, that temporary polarity that London dispersion forces give to a molecule. So the bigger the molecule, in other words, the more electrons, in other words, the greater the London dispersion forces polarity, that temporary polarity of London dispersion forces, all the electrons being pushed to one side, and therefore it sticks to other molecules better, other London dispersion forces molecules better. This gives I2 the largest London dispersion forces and F2 the smallest, because I2 simply has the most electrons. It has 106 electrons between the two iodine atoms, and fluorine has much, much less than that. This chart shows the boiling points of the first 4 diatomic halogens. 2 of the same type of atom will produce a nonpolar molecule, what we just said. Nonpolar molecules experience only London dispersion forces. As the number of electrons increases in the molecule, London dispersion forces become stronger. For this reason, I2 with the most electrons has the strongest London dispersion forces and the highest boiling point of the 4 halogen molecules. Okay, so that one's pretty straightforward. More electrons, more polarizability, which means that they'll have stronger London dispersion forces, so I2 will have the strongest because it's the biggest and has the most electrons. Now we're going to look at hydrogen halides. Hydrogen halides are diatomic molecules that contain one hydrogen atom and one of the halogens. So in the case of HCl, for example, you removed one of the chlorines from Cl2 and replaced it with a hydrogen. In the case of HBr, you removed one of the bromines from Br2 and replaced it with a hydrogen. Same with HI. You removed one of the iodines and replaced it with a hydrogen. Remember, hydrogens only have one electron, hydrogen atom. This means that the hydrogen halides have weaker London dispersion forces than F2, Cl2, Br2, and I2. Again, I2 has 2 iodine molecules. That's 106 electrons. How do you know that? You look at your periodic table. It's the atomic number. Whereas HI has 53 for the iodine atom and 1 for the hydrogen, so that's only 54 electrons. So I2 has twice as many electrons as HI, and therefore it has much stronger London dispersion forces because of more electrons. Since F, Cl, Br, and I have higher electronegativity than H, electrons are pulled toward the halogen, making the molecule polar. Polar molecules have dipole-dipole forces in addition to London dispersion forces. So now we have a molecule made of two atoms that are not the same. So the halogens are always going to have higher electronegativity, and therefore they're going to pull the electrons over. So the electrons go over towards the Cl in HCl, they go over towards the Br in HBr, they go over to the I in HI. That makes the halogen side more negative, the hydrogen side more positive. That gives it a polarity, and that's a dipole-dipole force. So these molecules have both London dispersion forces and they have dipole-dipole forces. The electronegativity differences of the hydrogen halides are, for HF, which is not shown on this chart here, but HF has a 4.0. That's actually, fluorine has the highest electronegativity on the periodic table. Hydrogen is 2.1, so the difference between those is 1.9. So that's a highly polar molecule. It has strong dipole-dipole forces. If we go down the periodic table, HCl is 3. The electronegativity for chlorine is 3, minus 2.1 for hydrogen is 0.9. So it has weaker dipole-dipole forces because it's less polar. Go down one more, HBr, 2.8 minus 2.1 is 0.7, so it has weaker dipole-dipole forces yet again. And finally, HI has the weakest dipole-dipole forces because it only has a 0.4 difference in electronegativities between iodine and hydrogen. Hydrofluoric acid is the most polar hydrogen halide, which means that it has the strongest dipole-dipole intermolecular forces. So hydrogen halides, HF, HCl, HBr, and HI have both London dispersion forces and dipole-dipole intermolecular forces. The order of London dispersion forces from strongest to weakest of the hydrogen halides is hydroiodic has the strongest London dispersion forces, followed by HBr, followed by HCl, followed by HF. It's simply the number of electrons. HI has the most electrons, so it's the most polarizable and has the strongest London dispersion forces. HF has the fewest electrons, so it has the weakest London dispersion forces. Now let's look at this, and then it should read, this is due to the larger number of electrons in HI. So now let's look at the order of dipole-dipole from strongest to weakest, and it's the opposite. It's exactly the opposite order. HF has the highest electronegativity difference. That makes it the most polar molecule, and therefore it has the strongest dipole-dipole forces between it and other HF molecules, followed by HCl, HBr, and HI. HI has the smallest electronegativity difference between hydrogen and iodine, therefore it has the weakest dipole-dipole forces. Hydrogen halides HF, HCl, HBr, and HI have higher boiling points than diatomic halogens F2, Cl2, Br2, and I2. This is because hydrogen halides have both London dispersion forces and dipole-dipole forces. The boiling point of the hydrogen halides decreases going from HI to HBr to HCl. So if you just look at the three over on the right side, HI has the highest, HBr is next, and HCl is next. We'll ignore HF for right now. So what is that telling you? It's telling you that the London dispersion forces of HI dominate over the stronger dipole-dipole forces of HCl. HCl has stronger dipole-dipole forces because it has a stronger polarity difference. HI has weaker dipole-dipole forces. However, HI has stronger London dispersion forces, and those tend to dominate. So it just shows you that you can't just assume that dipole-dipole is always stronger than London dispersion. In this case, the London dispersion forces are dominating over the dipole-dipole and giving HI a higher boiling point. This means that the stronger London dispersion forces of HI has more influence than the stronger dipole-dipole forces of HCl. So HI, HBr, and HCl have both London dispersion forces and dipole-dipole forces. HF has the highest boiling point of all the hydrogen halides. So now you look over to the left and you see that blue column is the tallest of any of the molecules there. HF has the greatest polarity of the hydrogen halides because it has the greatest electronegativity difference. This gives HF the strongest dipole-dipole forces. HF has the fewest electrons, so it has the weakest London dispersion forces to attract it. In addition, though, HF also has hydrogen bonding. None of the others do. So HF has the strongest intermolecular forces and the highest boiling point. So HF has all three types of intermolecular forces. It has very weak London dispersion forces, but it does have them. It has strong dipole-dipole forces compared to the others, and it has hydrogen bonds, which none of the others do. So it has all three types of intermolecular forces, and therefore has the highest boiling point. So here's a summary. So F2 has the weakest London dispersion forces and the lowest boiling point because it has the fewest electrons. Remember, those that are in the kind of the copper color there, they have only London dispersion forces because they're elemental diatomic molecules. I2 has the strongest London dispersion forces and the highest boiling points because it has the most electrons. HCl has weaker London dispersion forces than HBr and HI because it has fewer electrons, but it has stronger dipole-dipole forces because it has the greatest electronegativity difference between chlorine and hydrogen. Overall, it has a lower boiling point than HBr and HI. HI has stronger London dispersion forces than HCl and HBr because it has the most electrons, but it has the weakest dipole-dipole forces because it is the least polar. Overall, however, HI has a higher boiling point than HCl and HBr. So what that's telling you is the London dispersion forces in this case, not in all cases, but in this case, is dominating over the dipole-dipole forces. That gives HI with the strong London dispersion forces a higher boiling point than HCl, which has the strong dipole-dipole forces. Finally, HF has the weakest London dispersion forces of the four because it has the fewest electrons, but it has stronger dipole-dipole forces than the other because it's the greatest electronegativity difference. In addition, only HF has hydrogen bonds. These three forces give HF the highest boiling point of all hydrogen halides. Okay, now these graphs, you need to be sure you can interpret these graphs and what they're saying based on what we've just talked about. So stronger intermolecular forces cause substances to melt and boil at higher temperatures because the molecules stick together better and don't separate easily. So let's look at each of these four lines. Hydrogen bonds are the strongest intermolecular forces. Only nitrogen, oxygen, and fluorine with a hydrogen attached to them can hydrogen bond. So let's look at the light blue line. H2O has a much higher boiling point than H2S, H2SE, or H2TE. Now look at your periodic table and you'll see that O, S, Se, and Te are in the same group or column. So they all form H2 compounds. So these are very comparable compounds. But water has the higher boiling point because it is the only compound of those four that has hydrogen bonds. After H2O, then there's no more hydrogen bonds, so then it's again this battle between dipole-dipole and London dispersion forces, and what happens is that H2Te has the most electrons and the strongest London dispersion forces, giving H2Te the highest boiling point. So the strong London dispersion forces of H2Te overwhelm the stronger dipole-dipole forces of H2S because H2S is more polar. Now the red line. HF has a higher boiling point than HCl, HBr, HI. This was discussed in detail on the previous slides. Stronger IMF cause substances to melt and boil at higher temperatures because the molecules stick together better and don't separate easily. So let's look at the green line. NH3 has a higher boiling point than pH3, ASH3, or SBH3 because NH3
hydrogen bonds while the others don't. Again, nitrogen, oxygen, and fluorine are the only three elements that can hydrogen bond. And again, all four of these compounds are in the same group. So nitrogen, phosphorus, As, and Sb are all in the same column together. So these are comparable compounds. They all four bond with three hydrogens. Okay, now SbH3 has higher boiling point than ASH3 or PH3 because stronger London dispersion forces dominate the stronger dipole-dipole of PH3. So it's the same explanation as we've seen throughout this lesson. London dispersion forces are winning the battle against dipole-dipole. Dark blue line at the bottom. Now, the bottom line from CH4 to SNH4 contain only nonpolar molecules that have only London dispersion forces. The LDF are stronger because they have more electrons and higher boiling points. So SNH4 on the right has the most electrons, followed by GEH4, SiH4, and CH4. So the only forces involved in that dark blue line are London dispersion forces. So in summary, strong London dispersion forces are the result of more electrons. Strong dipole-dipole forces are the result of more polar molecules. And hydrogen bonds occur only with nitrogen, oxygen, and fluorine molecules with hydrogens attached to them. So intermolecular forces only determine if a substance is a solid, liquid, or gas. Intermolecular forces do not create new chemical compounds. A very important point to remember. All right, and that takes care of this lesson of learning how to analyze the intermolecular forces. This is definitely going to be asked on the AP exam, and you want to become very comfortable with making these types of analyses.